Yes, hey Krishna. So we are streaming this lecture on our YouTube channel too. So I think it's exactly 6. We should be good to start the session. By the way, hi everyone. Very good evening to all of you. And Krishna, would you mind to start the recording from your side?
Yes, sure. I'll start the recording. Yeah.
Okay, go ahead. Hi everyone, very good evening to all of you, and thanks a lot for joining to this webinar, which is quite a new topic or very defined topic, like comparison between quasi-static and dynamic powertrain modeling approaches. So that is using Matlab. So we have Krishna here today, so who is our simulation engineer, so who've been engaged in powertrain modeling for over 2 years now. So he will give you a fair idea on what exactly these things about approaches of modeling, and we will also run through the model itself that we have built in Matlab, so that we would just click through all the options and features, and then you can understand basically how these two modeling approaches are different. And we will also run through the comparison studies and why do we actually use different approaches for modeling, and that's all the stuff. So the objective is to kind of understand the differences with these two approaches, and how does the model look like, and what kind of results that you can expect, and why do you actually use specific type of models, right? So we won't be actually building the model, or you won't be actually building the model with us in the live, so because that would take more than about 10 hours to do that. So, but this is to understand the approaches to this webinar. So feel free and comfortable to drop your queries on the chat box. It would be really, really good if you're interactive, and because that makes the session quite exciting and also interesting across the whole discussions. So that's pretty much from my side. By the way, over to you, Krishna, to engage the session right here.
Yeah, thank you, Suraj, for introduction. Yeah. So, like as per our webinar topic, like comparison between quadratic approach and dynamic approach, we'll be discussing. So, yeah, I'll just start with the agenda of today webinar. Okay, before that, like myself, Krishna SH. So I work as a simulation engineer at Decibels Lab Private Limited. So with this small introduction, like we'll just start with the topic. So like as you see, the agenda of today's like webinar with respect to the powertrain. So we'll just go through the powertrain concept, the type of powertrain approaches, and the objectives like the required for it, and the overview of the models and the results comparison. So I'll just try to focus more on these modeling approaches as per in the agenda concept, like with the different approach, like how we can actually build the model, like the thing and advantages over each other. Okay, that will be that part will comes under here, and then I will go with respect to the overview of the models. Like directly I will take you to the Matlab thing, and I'll just run through the models, like how like in each subsystems, like how we are going to use the blocks and to build the model. That will be the one part, and we'll try to do some comparison results. So we'll just try to discuss like us like describing some different scenarios and how and what requirements we are going to expect from the models, kind of thing. Yeah. Like with this agenda, like I'll just move ahead. So, like as you know, the powertrain concept thing, like the what is powertrain? Like it's a basic thing. If you just try to remove this particular word, right, everything will be remained as a drivetrain. So if you include the source for your kind of vehicle body, that is nothing but like the vehicle dynamics part of your car, or like you will be involving like source for it, so it becomes the powertrain. The rest thing, if you just remove this source, it may be of IC engine, it may be of battery, based on your conventional or like EV or like vehicles kind of thing. So if you just consider this particular part, you can just figure it out with here. That is a drive lane, nothing but a drive lane thing. And the rest, like at the vehicle body, we can just define it as a sink. Okay. So whatever the power from the source you are getting, right? Like maybe it's IC engine or battery kind of thing from the fuel point of view. So at the end, you are converting the things into some mechanical power to it, and at the end, you will be considering as a sink. Okay. So if you just want to say like the components involved, the basic components involved in your powertrain things, the longitudinal dynamics part, like you can say that is a vehicle body, the differentials thing, the transmission things, and IC engine, or like in terms of, if you want to say in terms of electrical vehicle, or the motor controller, battery will play a part. Okay. Yeah. So with like as I was mentioning, like in terms of powertrain building, like we will be following some approaches. One is with respect to the quadratic approach, the other with respect to the dynamic approach. There are many other approaches, but I'm just trying to compare these two. Okay. So like how the model like is going to differentiate with different approaches, and what are the requirements for it, and the components involved in it. So by this, a kind of small basic flowchart, you can notice the things like longitudinal part of your vehicle dynamics, that is vehicle body, and the drive lane, transmission of the power, like transmission system, motor system, and the source system, that is battery, will be remained same in terms of your dynamic approach, where like you are going to sorry, this one thing, right? Yeah. So this is your kind of extra. I'll just try to use some yeah. This is a kind of another component like a driver model. It will be considered as a controller. Okay. So we'll deeply understand the what is driver model kind of thing in our latest slides. So if you see in the overall, like the common components involved in the powertrains, uh, while you are going for approach of quadratic, and also for going for or doing the modeling approach for dynamic. Okay. So with this, I'll just go through the first part of it, quadratic approach. This is a kind of schematic. Like you can just see the schematic thing. Initially, like we are going to input a speed, vehicle speed. You can just consider it as a reference speed. Here we'll be using drive cycles kind of thing to the vehicle body. And from the vehicle body, we are going to get the vehicle torque and the vehicle speed. There is nothing but the wheel torque and the wheel speed. We'll just discuss the entire thing once I run through the model. Okay. So later we'll be using some transmission system. From that, we'll be getting motor torque and the motor speed. And then from motor subsystem, you will be getting the motor power. And later, you are dealing with the battery. So by this, you can just consider that uh, we are going in a backward phase, right? By we can also say like quadratic approach. The other name we can consider it as a backward facing vehicle model. Okay, it means first we are considering that what are the requirements, what are the demanded by the vehicle body, like at the wheel side, like the considering that the longitudinal dynamics requirement. Okay, so based on the requirements, in order to like satisfy those requirements, we'll be like doing the like further estimations of with respect to the transmission modeling, motor modeling, and the battery modeling. So it means first we are just dealing that like estimating the requirements at the longitudinal part. Later we are going to size these components: transmission, motor, and the battery. Okay, this is like a backward facing vehicle modeling. Okay, so and there is another approach we were discussing, like so dynamic approach. Yeah, before going that, this is our like MATLAB model which we already built. So we'll just try to run through this model in a later stages of this webinar. And also we'll try to discuss like what are things involved in order to estimate these parameters in overview of it. Yeah. So this is one kind of quadratic approach, like one kind of approaching for model powertrain modeling. And the other approach, like a dynamic approach for vehicle body, or like forward facing model. Okay, here if you just try to compare with the powertrain, right, with a quadratic approach, all the components involved in it like more similar, except this particular thing we call it as a driver model. Okay, so the function of this driver model, the involvement of the driver model in this dynamic approach, we'll try to like discuss in detail. Okay, so here with respect to the schematic, right, if you are seeing like we are not going in kind of like backward facing or like completely with respect to getting the known things like well to wheel analysis, like we are not going for that approach. Here we are also feeding the same thing like as a reference speed, that is a drive cycle, and based on the requirements for the drive cycle to achieve the speed concepts or everything, we are producing some kind of value which will be considering based on our further model part, whether it is a direct vehicle body, whether it is a driveline dynamics. Okay, so based on that we are producing some values, so we'll be assuming those things for our further part of the modeling. Like you may consider that as a brake commands, acceleration commands kind of thing we are deriving with the help of driver model. Okay, yeah. So based on these acceleration commands and the brake commands, we are going to produce the torque demand. So with the torque demand and with the known available torque, how much like we are going to achieve the further things. Okay, uh, like if you know the torques and the torque speeds with respect to the motor, like we'll be dealing with the motor torque and the motor speed estimations. With that you can further go with battery sizing, but like with the help of transmission like we are going to again draw with here like required wheel speed and the motor speed. From that, like wheel torque and the wheel speed. From that, you are going to derive the force of it, and then from the force you are producing the acceleration. Okay, by using this particular equation, F is equal to m into a. So if you know like the torque equal to force into some displacement, right? So with this equation, you will be producing some force where torque you are going to get uh, from these blocks, and from force you are going to estimate this particular acceleration with knowing this data. Okay, from acceleration, you are going to estimate the speed and you are going to feedback. You can just consider it as a kind of feedback loop. Okay, here in layman language, if I want to say like what driver model exactly does, you are producing some speed. That speed has to be followed according to your reference speed. So in order to follow the reference speed, what are the requirements you are going to uh, achieve those things? So if you meet the requirements, then only like whatever the produced speed, it will be matched with the reference speed. Okay, this is we call it as like dynamic approach. Okay, so in later we'll just try to look into each subsystems of it, so we may get better understanding. Yeah. So if you have any queries kind of thing, you can just put those queries in the chat box. So just make this webinar kind of interactive. So the objectives like if you just want to consider, right, for the quadratic approach or the dynamic approach kind of thing. Yeah. Okay. The query is like, yeah, sure. So drive cycle, like if I want to say, is nothing but the velocity upon time graph. So yeah, like it will just try to, by this you can, you will be involving all your road characteristics, like in your day-to-day life when you are trying to write some point to point, right, from one point to the other point of your distance, you will be facing a traffic, pedestrian passing, like all things will be involved. So you're just trying, it is nothing but a velocity upon time graph. So with respect to the Srinivas, yes, okay. So we are just consider some kind of random motor, like we are not dealing much into the motor point of view, like a kind of equations we have involved. But for the EV thing, we'll be involving uh, three-phase motor itself. Yes. So can you drive it? No, the torque profile can be derived from the drive cycle with some data. Okay. So yeah, we'll just try to take these at last, or like these questions, queries. Okay. So as we were discussing about the objectives, like quadratic and the dynamic approach of the modeling, like the purpose like approach we will discuss like as I open the model, okay, in each, and the purpose, it is for the component sizing analysis, component sizing, and for the performance analysis, right? So component sizing is nothing but in order to like go for sizing, what is the exact requirement of your like motor torque, motor speed, motor power, battery power, current rates, kind of thing. So in order to achieve our required or the desired speed or the acceleration by the vehicle. Okay, a lot of parameters we are going to derive from the component sizing itself. So like how about like the performance analysis? Here performance analysis nothing but like in order to get the estimation for the acceleration requirements. So like if you just see in whenever the vehicle prologue light, so if you just see in the vehicle's specification data, they will be mentioning that like just consider a vehicle like 0 to 60 in 5 seconds. So it means like in 5 seconds it can go from 0 to 60. Again it will depends on the payloads and everything. Okay, so in order to achieve this condition, right, what are the requirements in terms of torques, the motor speed, or the power requirement at the battery side or the motor side, that we can study like with the performance analysis. Okay, so like as I mentioned, the objectives the same at the both ends means, but the thing is that the approach will be different in order to do the sizing components and the performance analysis of it. Okay, so yeah, I'll just take you to the model part. Later we'll discuss this modeling comparison. Yeah, first we'll just start with the quadratic approach. We'll just try to discuss some points in it in order to build like powertrain. Okay, yeah. So as I was mentioning, the schematic layout, this will be like dealing with the vehicle body, transmission system, motor model, motor controller model, battery. Okay, so here you will be like feeding back a kind of feeding the velocity. Okay, I'll just try to show you how the drive cycle looks like for some people who are new to these concepts. Let me run the model. Yeah. So this is your drive cycle. Okay. Here it is nothing but velocity upon time graph. So as the time progresses, like you will be like dealing with some different velocity profiles. So how it can be helpful for your motor sizing or battery sizing, just try to think in analytical pattern. So if you want to design like motor for this particular speed, okay, like let's say like you are moving with some 15 kilometer per hour, so what are the requirements of the motor torque or the motor speed, motor power or the battery power? And if you want to design for this particular speed, like approximately it's moving like 70 kilometer per hour, so the requirements will be different, right? So in order to for the different speed values, like we had to design the motor requirements, right? So for that we'll be using the drive cycles. Okay, so here in terms of like drive cycles, we will be feeding into the vehicle body, and here in the vehicle body we'll be like calculating the requirements at the wheel side for your vehicle to move. let's say kind of a body. Okay, so you will be like, in order to move this particular vehicle, right, initially it has to undergo some uh, like it has to overcome some resistive forces. You may be like, you may say like aerodynamic force, resistive forces at the wheel side because of it is in a contact with the road, and then a kind of gradient force if the road is uphill condition. Okay, so those have to overcome, and then it has to move, right? So for to do these estimations, like we will be like calculating all the resistive forces, aerodynamic force, rolling force, gradient force, and this acceleration force, like it will be a traction thing which will help you to move the vehicle. But we don't know like how much is required in order to achieve the different set of velocities. So for that we will be adding this particular force also. So adding all these resistive forces, like we are going to get the wheel torque and the wheel speed, which is derived from the velocity. Okay, so as I mentioned, like if you know the force, like torque equal to F into a kind of displacement or the distance, you are nothing but your like distance is nothing but like radius of the wheel. Okay, you will be getting like torque. So with this, like you are going to get the wheel torque and the wheel speed. So if you know at the transmission modeling, with the transmission efficiencies and the gear ratios, like which already will be the design values, or you can also get those values by modeling based on our requirements. Okay, like it will be designed based on our torque requirements and the speed requirements. This particular gear ratio values. So those will be like with these you can get to know like motor torque and the motor speed, because transmission like it is the component which will be like connecting from wheel to the motor, motor to the wheel. Okay, in EV, like most of the time for two wheelers, if you just go for hub motor, you won't be requiring those things, the transmission system. Yeah, so yeah, this is with respect to the motor modeling. So here in the motor modeling, like we are going to calculate the motor power with the help of motor torque and the motor speed. If you remember the basic equation, like P is equal to 2 pi nt upon 60. Okay, so again you are dividing with some motor efficiency. Okay, and you will be getting motor power. Here, before dividing the motor power, whatever the power you are getting, right, that will be considering as motor output power. If you divide with the efficiency, you are going to get as a motor input power. Yeah, these are some like basic concepts and kind of. So here, like we are going to divide with efficiencies, like where the efficiencies, where the function of like motor speed and the torques. Like your efficiency of your motors will be varying based on your motor speed, motor torque, and even sometimes the temperature is also going to affect. From the motor, again you are going to divide like with the motor controller efficiencies. At the end, you will be going for the motor power and the motor region power. So this term, like we'll just try to discuss in the other thing section or thing. Yeah. So this is with respect to the battery modeling, where you will be going for estimating the SOC of your battery like energy and energy consumed per kilometer, battery power, battery currents. Okay, I'll just try to pinpoint those things. Energy consumed, battery energy, and SOC from this particular block. Okay, and battery currents and battery C rates. Okay, so with these known data, further like you can go for like calculating the cells in series, cells in parallel, and total number of cells required. You can also estimate like the energy required, oh, like for the per kilometer with region and without region, that you can discuss. Okay, so these are some kind of parameters which we can calculate. It is some kind of straightforward with this approach. Okay, so whatever the requirements at the wheel side, like in order to overcome the whatever the environment it's like it is just giving some resistance for your vehicle movement, right? So we have to estimate those things, and we have to decide like what are the requirements or the desired with respect to the motor and the batteries in order to overcome that resistances. So this is a kind of straightforward. Okay, like based on the requirements you will be calculating at the source side. Okay, this is like a backward facing approach, quadratic approach. So I'll just quickly move to the dynamic approach. Here in the dynamic approach, the same thing, we are going to give the reference speed, and in the reference speed like this is nothing but like a reference speed to this particular driver model. I just try to open this model. Yeah, so here we will be using some kind of controller. We call it as a PID controller, where P means proportionate, I means integration, D means derivative. Okay, so here let's like I'll just try to take some scenario and try to explain this concept here. Here your reference is like some kind of like 100 speed kilometer per hour. Okay, here you have like actual speed is of 90 kilometer per hour. So the error is somewhat of like 10, right? So in order to eliminate that particular value, what value it should be produced? Okay, so in order to eliminate that error, right, it's going to produce some values. So that value we can further later consider it as the acceleration command or the brake commands based on our further model part. Whether you are directly dealing with the vehicle dynamic part or you will be involving all your driveline system. Okay, and yeah, so you will be like giving the acceleration commands and the brake commands. So based on your acceleration commands and brake commands, you are going to produce the demanded torque. So once you know the torques, from the torque you are going to derive the speed. From if you know the torque, from the torque you are going to derive the speed. like not speed, a force. If you know the force and total net force for the demanded torque, this is your the force required in order to achieve the demanded torque. So from this force, you are going to like subtract all your resistive forces. Like it is nothing but F is equal to M into A. Yeah. So from this, like the force, if you just try to subtract all this force, you will be remaining again with the force. So just divide by M, and you will be dealing with the acceleration. So if you integrate the acceleration, you will be getting the speed. Okay, that speed somewhat it has to reach, or like somewhat it has to match with the reference speed. So initially, like it won't be matching. So with this help of this controller, we have to tune in such a way that it has to match. Again, it depends on the available torque values and the motor values, which we already defined. Okay, this is some kind of approach. I know like it's very hard to digest. Yeah, the equations or like they involved in the modeling, right? Like the most of the equations like will be similar with respect to the quadratic approach itself. So further with respect to the battery thing and the motor control and battery thing is the same. From this particular part, from this here, yeah, or like you will be like just interchanging the equations in terms of RHS and LHS. So yeah, like it's not like in terms of EV industry kind of thing, like currently using here, it based on the requirements. So if you want to say like based on our requirements, like what we have the data, so how for our up to our comfortness, like we can go for uh, doing these particular approaches. So if you want to say like the accurate approach, if you want to reach, that is you can go for dynamic approach, or like you can get the exact results. Like I'll just try to show those things with try to changing with some scenarios. Okay, so I'll just try to open this quadratic approach. I'm just trying to run the model. Yeah, so I'll just try to see some results. So this is your aerodynamic force, exponential force, rolling force, and gradient force. And if you want to see like wheel torque, these are the wheel torques and motor torques. So these are like you can see the spikes, right? And these are some kind of like continuously as mentioned here. So it will be like depends on your speed profile which you are giving as a drive cycle. So we know that one basic concept, that is torque is directly proportional to the acceleration. Like yeah, and it is like how if you want to say like you know that torque you can derive it from the force. Okay, yeah. So indirectly you will be like force is directly proportional to the acceleration thing. Yeah. So here it will be like wheel speed and the motor speed. So motor torque and the wheel torques. The pattern will be remain same, the appearance of it. The wheel speed and the motor torque or motor speed. These are some of motor power and the battery power. Yeah. So here, like with respect to the motor controller, right? Like okay, let me start with the motor controller thing. So motor controller here we just like defined the efficiency of your motor controller. You know, right? Like motor controller, it will be like having some capacitors, resistors, and some other components, MOSFETs kind of thing. Whenever if you're trying to pass some energy through it, like they are getting heated up. So whatever the heated things they are going to emit that into the environment is nothing but the loss, right? So that loss again, like it will depends on your motor torque and the speed values. It is how I'll just say, like torque is directly proportional to your current, and speed, motor speed is directly proportional to the see, motor torque is directly proportional to the current. Motor speed is directly proportional to your voltage. Okay, so higher the torques, you will be dealing with the higher currents. So if you're going for the higher speed and the power requirement, you have to deal with the higher voltages. Yeah. So by testing, like we'll get to know this lookup table data. Okay. So here you will be getting some efficiency values based on your motor speed and motor torque. I just tried to show one in lookup table inside of it. Like you will be dealing with motor control efficiency, where it is a function of motor speed and the motor torque. Yeah. So quickly, I'll just take you through the dynamic approach. You'll try to focus more time on this approach, or like I just want to say, like it is a more efficient than your quadratic approach. So here, like I'm selecting this particular profile, NEDC profile, and I'm just trying to run the model. Okay. Here, this is with respect to the reference speed, drive cycle speed, and this is actual speed. So if you see this particular graph, right, this blue one, it is with respect to the reference speed, and the yellow one is with respect to the actual speed. Actually, you are not able to view the yellow. It is because of overlapping. So if I just make the blue one as off, you can view these yellow, this particular actual speed. Okay. Yeah. So we just try to play some like scenarios, like how we are going to reach the things. So in the motor model, like I will be dealing with some equations here. So I will be assigning some available power and the torque, available torques for the motor thing, and based on that, the demanded acceleration. Uh, like it is also possible in the Scilab, but the thing is that it is because of high competency, it may lag in the Scilab. So if you just wanna see, like, yeah, here initially I will be like assigning some power, right? You can just say 50 kilowatt. Okay, I'm just going to reduce it by 10. I'll just say as 10 kilowatt. I'll just select this graph and let the model run. So now you will be facing some kind of like estimating the actual speed comparing with the reference speed, right? If you see, let me show you. Yeah. So as you go at the highest speeds, like you are not able to reach the required or the desired speed as per the reference speed. Your blue is nothing but like actual speed. Okay, so yellow is your reference speed. So here like your actual speed is not able to reach the reference speed. It is because of available power is not efficient to produce the motor speed or the motor torques at this particular region. Okay, so we'll just try to consider this particular region. Approximately like the blue like that is actual speed is trying to reach the reference speed at this here. See this at some particular time, let's say like at 800 and or like 850th second, your reference speed is at 70, where 860th second your like approximately like it's taking some kind of 10 or 20 seconds delay in order to achieve this reference speed. It is because of available power is very less. Okay, so I'll just try to show you. So I'll just try to make it less again. Let's say like 50 or 5 kilowatt. Let me run the model with comparing the velocity. Yeah, this you are going to like face. It's not able to reach the required the velocity. It is because of not having sufficient power. Okay, so you can just start increasing the thing. I'll just start with 20 kilowatt. I'll just say run the model. So you can see here. So still some kind of error is there. So in order to avoid that error, again have to increase some more power. Let's say like 25 kilowatt. Yeah. Let me run the model. Yeah. So somewhat like some error is has reduced. Again, you'll just try to increase some more power, like 30. I'll just try to run. Yeah. So like you can reduce the error like based on the power requirements. If you exactly assign the required power here, so by this you can go for like estimating the motor power kind of thing. So in order to achieve or like the requirements from the velocity profile, again with respect to the torques, you can see here, yeah, these are some kind of motor torques. These are like required in order to achieve that particular uh, acceleration which is in the velocity profile of the speed requirements. So with this you can also estimate like motor like motor torques and the motor speed, motor power for the in terms of performance analysis. Okay, we'll just try to go for this particular speed profile. So this is somewhat like 80 km per hour. Okay, we'll just consider it as 80 km per hour. I want to achieve like in 5 seconds. So what are the torque requirements or the speed or the power requirements? Okay, for me the available power is somewhat, let's say I'll just try to change like 20 kilowatt. Yeah, here I'll just change the profile one, say okay. I'll just make it 50 speed time. Now let me run the model. So here for reference speed is at 80, right? So in order to reach this particular speed, yeah, so it is approximately taking some 18 seconds in order to reach this particular speed, right? So I had to increase some power here. The requirement power is high. I'll just say like 50. You can see here. Yeah, let me run the model. Yeah, now you can see the power requirement, like as you increase the power, available power. Uh, so now you can achieve this particular speed about some 6 to 7 seconds. Okay. Again, I will try to increase. Let's make it 70 kilowatt. Yeah, approximately like you are reaching the required speed at within a 5 seconds, like at 5 seconds, right? So with this, you can size your power. So this is some kind of available power, and you can deal with the torques ratings. So region braking power, it depends on how like how much the brake force you are applying on it. Okay, so here in the velocity profile we are not doing any braking thing. Yeah, we are just using the traction thing. Okay, yeah, so this is some kind of torque requirements. You can see here up to 5 seconds, like up to for some first 3 to 4 seconds you will be requirement of 160 newton meter as a torque, and later your torque is going to decrease as the motor as your vehicle speed reaches the 80. Okay, so you know like higher the speed, lower will be the torque requirements. So you can see the torque values even if you like so if I change the torque limit, let's say like you just keep it as 100 and let me run the model. So as you limit the torques, like you will be like the requirement of the torques of it will be like 5 seconds continuously requirement of 100 newton meter to achieve that particular speed values. So even you will be see some difference in terms of speed. Okay, see, earlier it was like at here, even if you limit the torques, it will take some more time to achieve this particular required speed. Okay, so this is how you can go for torque, motor torques estimations, motor power estimations, and the speed estimations kind of thing. So here in the dynamic approach, right, you can readily start with the performance analysis. It will be very easy to do the performance analysis, which we done now. If you want to deal the performance analysis in terms of quadratic approach, like you will require the acceleration data, which you have to collect it from the real time testing, or like which is already available, acceleration drive cycles kind of thing. Yeah, again those will be depending on based on your different vehicles kind of thing. So with respect to these approaches, like if you have any queries, just let me know in the chat box. I hope you got some difference of these approaches, right? The purpose of the quadratic approach, why we has to go with the dynamic approach kind of thing. Yeah, just let me know if you have any queries.
Krishna. So, by the way, great session overall. Uh, so, thanks for bringing quite a lot of clarity by going through the model and also showing something that is definitely possible within the time span. Um, so, if you guys have any questions, the floor is open for QA.
So, like Srinivas says, yeah, here dynamic model motor controller. Here, if you just consider the motor controller, right, we are not dealing any like controller part of it. We are just estimating the efficiencies. So, you know, right, like whenever you are transferring the power from battery to the motor, there will be some kind of motor controller in between. So like there will be having some losses. So those losses we are including in this motor control model. Yeah. So this is like motor controller thing. We are not dealing with like motor like algorithms kind of thing. This is some kind of thermal point of view. Yeah. The losses estimation point of view. Yeah. In terms of like briefly, I want to summarize, right? Here, quadratic approach, it will be like some kind of backward. So you will be getting some straightforward. So if you want to start learning the powertrain design kind of thing, you can start with the powertrain quadratic approach. So in order to learn this thing, like you required some basics of it. So yeah, that is the one thing. And in terms of quadratic and the dynamic, like it will be very easy to like to understand the performance analysis of your vehicle and also the sizing, and it will be very accurate compared to the quadratic, like based on the available powers. By assigning the available powers, you can deal with the requirements in terms of motor torque requirements, speed requirements, or that the battery sizing requirements. Yeah. Can you just like briefly elaborate that SPWM, like what exactly it means? Yeah. Anyone have any questions with respect to? Actually, I'm not getting like what you're trying to say. Like sine, pulse, with thing, right? Those will be completely with respect to the electronics point of view. This is with respect to the sizing point of view. Yeah.
Right, Krishna. So
Okay. Yeah. There are some questions. Like there will be completely with respect to the algorithm point of view. Yeah. So you will be like dealing with in other things. Yeah.
Right. So great, Krishna. I think we could summarize the whole session by now. So by the way, thanks a lot, everyone, for attending the session. It was great to host you today at this webinar. I believe you might have gained some good exposure by the session. So kindly share your feedback before you leave the session. Share us how was it, and did it meet your expectations, or are you expecting some other topics in the future? So please do drop the details on your chat box, and that would be very important for us to host the upcoming webinar series such they can help you. So by the way, thanks Krishna for delivering the fantastic session, and thanks a lot everybody for participating in the lecture series and in the webinar series. So cool. There is a one question. Can we share the model? No, we do not share the model. Okay, so thanks a lot, everybody, again. So kindly share your feedbacks before you quit the session. Thank you.
Yeah. Just a second, Suraj. Like I just want to say at the end, this powertrain modeling, like quadratic approach or the dynamic approach, these are just like whatever we build. It is for just in a sizing point of view and performance analysis point of view. Okay. Like we are not involving any components algorithm like which you were expecting like in terms of various questions. Yeah.
Right, Krishna. Yep. Okay. All right, guys. So we have the recordings available on our YouTube channel. The live session will be available there. So feel free to jump in there and take up the recordings of the session. So great then. Thanks a lot, Krishna, and thanks a lot, everybody. And good evening to all of you. And thank you again. Take care. Bye-bye.
Thank you. And thank you, Virendra. Yeah.